Welcome back to day 68 of Daily LeetCode. Daily LeetCode. It's quite late, but we're on Californian time, so technically it's very late still in Californian time. So yesterday we had a legendary comment from I'm Just That Guy, no hat type of day. True. Very, very true. I actually had quite the mammoth cut underneath the hat, but I also didn't think I'd ever show my forehead on the internet, but I've been exposed. And then Thomas mentioned it's going to fast and so point. I would say this is the ultimate 2-pointer question. I agree. It's also a pretty fun question. So I kind of want to do another string question. But that being the case, you still have new problems to do. Also going to keep the timer short because as always, minimum is always 20 minutes, to be honest. That's what we started with. So maybe that's what we should do, but we're going to do 30 minutes anyway. So I'm just going to jump into it. This video is going to be called No Days Off 2, or No Days Off. Actually, it's going to be a surprise what this one's called. But we're going to start with kth smallest element in the BST. So given the root of a binary search tree and an integer k, return the kth smallest value, one index of all the values of the nodes in the tree. So this is interesting. So we're given a BST, right? 1, 2, 3, 4, or 3, 1, 4, 2. They'd like us to return the 1th element, which is really the 0th. Oh no, they'd like us to return the kth element, which is really the 0th element. Wait. From the kth smallest value. Oh, right. So the 1th element, or the 0th element, or the first element, right, in this BST is going to be 1. And the reason that's the case is because the smallest value, right? So that's kind of the key. In the BST, in order, traversal of a BST equals array in ascending order. Since that's the case, if they want the kth smallest value, we just have to get the array in ascending order and give them the k minus 1th element because it's 1 indexed. So we need to turn the root into an array, then subscript it with k minus 1, right? So to do that, we could create an array to start. We could call a method, right, called traverse, pass in the array or the root in the array, and then we could return r sub k minus 1. Now the goal with traverse is that it just produces or it adds elements into the array to create an in-order traversal of the BST. So to do that, we're going to need an access to the node. So we'll call it node, which can be tree node, or null, or the array, which can be an array of numbers, or void. We're only going to be interested if node exists, right? Because is it possible for our tree not to exist? It's not possible. Our BST will always have at least one node in it. So if the node does exist, we're going to say in order is a DFS, right? Where in order refers to the order of the nodes or the relative order of the processing of L, N, and R. In order means L, N, and R. So to do that, we have to call traverse to node.left and array. Then, right on this node, we could do r.push node.val. Then we'll do node.write. So this will be done in linear time with linear space. So given an integer array nums, move all zeros to the end of it while maintaining the relative order of the non-zero elements. Note that you must do this in place without making a copy of the array. So let's map our problem statement to the example. You have an array nums, and move all zeros to the end of it while maintaining the relative order of the non-zero elements. So if you move all zeros to the end, then we have 1, 3, 12, 0, 0. Right? And it seems that our array always has at least one element in it, right? So how can we go about solving this? We take 0, right? What if every time we have a 0, we'll swap it? We'll keep track of that 0 index and swap it, right? What if we keep a rolling window of zeros to the end of the array? If we had this 0, we'd swap it with 1, then 0 would be here, right? But then we have 2 zeros. So we want to swap this 0 with this 3, right? And so this is kind of what it would look like to start. So we'd swap this 0 and this 1 to get something like this. Then we have these 2 zeros. We're still keep track of this 0's index here. And then we'd swap this 3 and this 0. Then we'd have this 0, right? We want to swap 12 and this 0, right? So it looks like we're always going to be incrementing this variable called LZI by 1 to keep track of our 0 index. Right, so maybe we can have a variable called let LZI equal 0. Right, and we'll say let I is equal to 0. I is less than nums length I plus plus, and we'll say if num sub I does not equal 0, right, but we only want to swap if the value doesn't equal 0. So if there's no 1s or no non-zero values, then we won't swap it. We want to swap temp equal to num sub I. Num sub I is equal to num sub LZI num sub LZI equals temp, then we'll say LZI plus 1. This would be done in linear time, but I'm curious why we can't say this fails if we do LZI equals, oh, not num sub 0. If we set this equal to actually 0, it should work here but fail on a future case. Oh, it still works. So, okay. So we're given 2 integer arrays, nums1 and nums2, sorted in non-decreasing order, which means ascending order, and 2 integers m and n, representing the number of elements in nums1 and nums2 respectively. Merge nums1 and nums2 into a single array sorted in non-decreasing order. Finally, sorted array should not be returned by the function, but instead be stored inside array nums1. So comment this, num1 has the length of m plus n. The first m elements denote the elements that should be merged. The last n elements are set to 0. Should be ignored. Nums2 has a length of n. So we're basically merging arrays nums1 and nums2 into nums1. So we're basically merging nums2 into nums1. But the output should still be an array sorted in non-decreasing order. Given nums1 that looks like this, and nums2 which looks like this, nums1 has enough space for both m and n. Should come out sorted. So it's possible that nums1 can have a value and nums2 can have no value, and vice versa. Right. I think the thing that makes this difficult is that the source array, we're merging it into the source array. we're merging nums1 and we're basically merging nums2 into nums1. Right, so we don't have to return anything, but I think what makes it difficult, if we could just copy nums1, then we could just merge temp and nums2 into nums1. So we say temp is equal to nums1, but then we just have to merge temp and nums2 into nums1. Now we can overwrite the values in nums1, which simplifies the implementation. So to do that, we just have to take the smallest value between nums1 and nums2, right? So we'll have 2 pointers. P2, P1 is going to be the pointer in temp, and P2 is going to be the pointer in nums2. But since we're going to be copying elements from either into nums1, we're going to want P3. Actually, we can probably compress this into equal to 0, I is less than nums1 dot length, I plus plus. This will be our third pointer, since at each index we're going to have to take the smallest element between temp and nums2 and put it in nums1 sub I. So this would look like if if temp sub I is less than nums2 sub I, right, then we want to copy that value into nums1. So we'd say nums1 sub, and actually we don't want to use I here, we want to use P1, right, and P2, which will change depending on which values we take from each array. So we say nums1 sub I is equal to temp sub P1, and we do P1 plus equal 1, and then we can do else so P2 plus equal 1. And the other thing we have to, I think, check, right, we need to also funnel elements, right? So temp sub P1 is less than nums2 sub P2, right? If 1 less than 2, then we copy 1 right into nums1, right, and then so on. But there's a problem, right? What if the first array is empty? So what if nums1 is empty, right? I don't know. What if nums2 is empty, right? In this case, if nums2 is empty, in this case, right, nums1 is 1. We'll check if 1 is less than undefined. Since 1 is not less than undefined, then we actually do this line here, but there's actually no elements. And I just realized it should be nums2. There's actually no elements in nums2 to copy, so that's a problem. To fix that, we also want to say if temp sub P1 is less than num sub P2, or temp dot P2 is greater than or equal to nums2 dot length. All right, so if P2 is 0, right, and P2 is greater than or equal to 0, then we want to just shove the remaining elements in nums1 into it. Remaining elements in nums1 back into it. So our output isn't looking correct. Could we do copy 1? I wonder if our copy is incomplete. Let's check. I'll go until I is less than 6. Let's say temp sub p1 is 1 less than 2. Yes, we copy 1 in. Right. Now we're going to say it's 2 less than 2. No, so we copy times 2 in. And we're going to say it's 2 less than 5. Yes. And we're going to say it's 3 less than 6. Yes. Right, we never get to undefined because there's too many elements in temp. So we basically only want to copy the values in temp up to one.slice m, not slice. Let's see, so I think this takes O of m time to copy the values in the temp. And we also use a space of O of m, and then the time complexity would be m plus n. We're going to string s containing just the characters open, closing parent, open curly, closing curly, opening bracket, closing bracket. Turn the input string is valid. Input string is valid. Open brackets must be closed by the same type of brackets. Open brackets must be closed in the correct order. So we basically want to make sure that parentheses are valid. They're closed by the same parentheses and they're closed by the same type as well. Here we can see a breach of both rules. Oh no, a breach of the first was must be closed by the same type of bracket. So if that's the case, right, they don't show us here, but a potential case, right, is that we could have something like this, in which we still want, this would still be valid because it would be closed by the same brackets and in the correct order. So I think what we want is something like a stack where every time we add, we find an opening character. Every time we find an opening symbol, we'll add it to a stack. And whenever we find a closing symbol, we'll try to match it to the top of the stack. And if they match, then we can pop it off the top of the stack, pop it, and if they're both, if the stack is empty, then we should have a valid parenthesis. To start, we'll have a stack. We're also going to need to tell when something is an opening symbol. To do that, we're going to need a symbol map. We can say new map This should give us what we're looking for. And we can iterate over the, we'll say const sim of s, right? And we'll say if, we can call this symbols. We'll say if symbols.has sim, right? Then it must be, because we're mapping opening symbols to closing symbols. And now if it has it, it must be an opening symbol, which means we're going to want to push it onto the stack. And then if it's not an opening symbol, it must be a closing symbol. Right, and so there's a case you want to check. If it's a closing symbol, right? So it must be a closing symbol, right? Now if the stack length does not equal 0 and, right, we're closing the correct bracket. So let's just say we're closing, we get this square bracket, right? We're going to want to make sure we're matching it to this open bracket on the top of the stack. So we're going to want to say stack sub stack dot length, right, -1, which will give us the last element in the stack, right? We're going to want to figure out what its closing symbol is. We'll say symbol dot get, right? We'll have a closing bracket for this, right? We know if we're in this else if, right, that we're talking with the closing brackets. We're going to want to say if it equals this sim, we can do stack dot pop. Otherwise, we know we're breaking either of the two rules, right? If they matched, we pop, so they must not match, right? Or if the stack is empty, then it must be false. Or the stack isn't empty, we get the symbols and they don't match. So we can return false. If we make it all the way down here, we'll return true. So for a singular bracket, right, for a single bracket, we return true, and that's because we never find a closing bracket, right? Like we said, we want to make sure that the stack is equal to 0. This would run an O of n time, where n is the number of opening symbols in the string, and since the number of opening symbols can just be a bunch of opening symbols, right, the worst case is n, right, and same, since all these opening symbols will go on the stack, will be O of n time and space. There's 6, and I'll just try a random problem. This looks complicated, so we'll skip this one. This also looks complicated. Oof. Okay, let's just pick one. Try an iterator to flatten a 2D vector. It should support the next and has next operations. Implement the vector 2D class. Initializes the object with a 2D vector vect. Next, returns the next element from the 2D vector and moves the pointer one step forward. You may assume that all calls to next are valid. Has next returns true if there are still some elements in the vector, and false otherwise. This doesn't seem too bad. So if we have vector 2D, now we have a matrix of 1, 2, 3, and then 4, right? Right, so we say next 1, next 2, next 3, right? Has next true, has next true, next is 4, has next false. So I think has next could be solved right in constant time. If we add all these values to an internal vector, we can just count how many values we have. Whenever we do has next, we'll just check if a particular number indice is less than the number of values we have. The next portion is a bit funky. But we could start by copying, we call it a vector. It's an array of arrays. We'll just say it starts with an empty array to start. We're gonna want to copy this to our array, so say for cons row of vec, call of vec, equals this, and then we're going to say for, this would be the row, say for cons num of row. I guess we can actually, yeah, we'll just say let's say this dot vector dot push to copy it, then we'll just print vector. Just to start. Okay, so it looks like our copy does work. And then for next, we have no time or space complexity, moves the pointer one step forward. So I think what we could do is just keep a stack of tuples. This will be the number of elements in the, this will be the row and the number of elements in the row. All we have to do is check when we do has next if there's a next row available, or if the number in that row is not 0. So we'll do is just say .stack.push r plus equal 1. So we'll push r and then row dot length. And then when we say next, we'll just return So this dot vector sub this, I guess we can say this dot stack sub, or I guess we can say right, and so we'll have a row. And then we'll say, we'll try to get the row that we currently have. Then we'll create a new row and we'll say we can just make a function called next row. We'll call it next index, and it returns an array of numbers. This is well this dot stack not equals 0, and this dot stack sub 0 actually this one is sub 0 sub 1 equals 0. Then we're going to say this stack dot pop, otherwise it's going to return this stack this dot stack sub 0. So when we get next, we can just say just not next index, and then we can return row, right? And let's just say this has 2 elements in it. What we really want is this dot vector sub row length minus column. Has next, right? We'll say return this dot stack dot length not equals 0. Minus 1 then we'll use column, we'll just add 1 to it. Oh, I guess you can always just do -1. Okay, what is going on? Guess we just have to wrap it if this dot stack dot length I don't understand. Next. If we remove every nonsense code I just wrote, what has it wrong is this has next part. So if the stack is empty, just return -1 and -1. Then when we call next index, if row equals -1 or call equals 1, we want to return oh, I'm realizing now it's just this dot vector sub row. And we don't even have to add 1 to it. I overcomplicated this. Could have just stored it in a flat array. Yeah, that took way too long.